Hello everyone, welcome to the fourth week of this semester. In this week, I'm going to start chapter 3, Transport Layer. As you know, which is about
Transport layer is
the
the
transport
fourth
layer.
layer of computer
Transport layer, as
networks.
you know, is the So our goal in this chapter is to understand principles behind transport layer services like multiplexing or demultiplexing. We also want to know um, what are the principles for reliable data transfer and how transport layer can help computer networks to have reliability in data transfer. And also we talk about flow control and congestion control, which are two other services that transport layer offers. Obviously not all the protocols in transport layer offer these services. Some of them offer congestion control, some of them offer flow control, some of them have reliability services, so but we are going to talk about all of these all of the principles behind these services. Also, we learn about the internet transport layer protocols, which are UDP and TCP. UDP is a connectionless transport layer protocol, while TCP is a connection-oriented, reliable transport protocol. Also, we'll talk about TCP congestion control. Obviously, I'm not going to go over the whole chapter 3 in this week. For this week, we go over the first half of chapter 3, and in the next week, we finish chapter 3 material. As an introduction to transport services, we can think of a transport layer as a tool to provide logical communication between app processes running on different hosts. So, in summary, you can think of a transport service as logical end-to-end communication between processes running on the host all over the world. So, in one side of the communication, we have one process running on one host. On the other side of the communication, we have another process running on another um, host. So when the processes are running, they think of transport layer as a black box that can provide communication between the processes. So that's why we say transport layer provides logical communication between app processes. So how does transport layer or transport protocols do this? How can they provide end-to-end communication? The sending side, which is the sending process, breaks the messages into segments and passes it to the network layer. So the sending process wants to send a message to the receiving process. So first we have to break that message into smaller chunks, which we call them segments. Okay. And then we pass these segments from the fourth layer, which is transport layer, to the layer below it, which is the network layer. On the receiving side, so here is the sender side. As you see, we have transport layer here. That's where the transport services are provided. And when we have an app message in the fifth layer, we break it into segments, and each segment in the transport layer is transferred to the network layer, which is one layer below the transport layer. And then after that, the data is transferred all the way to the receiving side, In the receiving side, uh, we have similar process but in the opposite direction. First, the transport layer receives segments, and then it assembles those segments to reconstruct the app message that the sending side was supposed to. I mean, the sending side intended to send to the receiving side. So in the application layer, we assemble the segments and reconstruct the message the sending side sent to the receiving side, to the receiving process. So in the receiving side, we reassemble segments into messages, and then after we do this in the fourth layer, we pass it to the fifth layer, which is the application layer. There are multiple transport protocols available to apps. In the internet, the two most famous ones are TCP and UDP, which we go over them in detail in this chapter. If we want to summarize the difference between transport layer, which is the fourth layer, and network layer, which is the third layer, we can say that network layer provides a logical communication between hosts, between two computers on two end systems of the internet. However, transport layer provides logical communication between processes. The processes are all running on different hosts. Every process must have a host that runs that process. A host may have multiple processes. So, in the transport layer, we need to rely on the services that network layer provides. Why? Because in the transport layer, we are dealing with processes, and these processes are running on the different hosts. So we have to rely on network layer to provide the communication between hosts. And also in the transport layer, we enhance the services that network layer provides. For example, network layer doesn't provide reliability. So in transport layer, we can add reliability to the services that network layer provides, and this way we can have a reliable data transfer. In order to illustrate the difference between transport layer and network layer even further, I'm going to explain this household analogy in the book. Let's assume that there are two houses in different parts of a city. One is Anne's house, the other is Bill's house. In the Anne's house, we have 12 kids. In the Bill's house, we have another 12 kids. So you can think of Anne's house and Bill's house as two hosts connected to the internet, and the 12 kids in Anne's house can be considered as the 12 processes running in Anne's host, and the 12 kids in the Bill's house can be considered as another 12 processes in Bill's host. Now let's assume that these 12 kids in Anne's house want to communicate with the 12 kids in Bill's house using letters in envelopes. So let's assume that one of the kids in Anne's house wants to send a letter to another kid in Bill's house. So for such letter exchange, we need to have the service that postal service provides, right? Because Anne's house is in one part of the world, Bill's house is in another part of the world. So we need to have a postal service that can carry the letter from the source to its destination. So that's similar to what we have in internet as network layer protocol services. Okay, so network layer protocol services can be considered as the postal service that we have in this example. However, we need one more service. In both Anne's house and Bill's house, we need someone to distribute letters among kids, because every letter is sent to a specific kid in Bill's house, for example. So there should be someone or some service that can distribute letters to the right kid in Bill's house. So when a letter arrives in Bill's house, someone has to read the recipient of the letter and passes it to the right kid, right? In the same way, we have to have the same, a similar service in computer networks. When a message is received in Bill's host, there should be a service which we call a transport layer service that can choose the right process among the 12 processes that we have in the receiving side, and passes the data to, or passes the message to the correct process that the server, that the sender aims to transfer messages to. Similar service is needed in the sending side. In the sending side, we have 12 processes in one host, that one of them wants to send a message to the receiving side. So we need to have another service in the transport layer that can gather all the letters from all the kids in Ant's house, or all the messages from all the processes in Ant's host, and transfer it to the other side of the network, which is the Bill's house, or the Bill's host. Here you can see some of the services that TCP and UDP provide in internet. As I said, TCP and UDP are two famous internet transport layer protocols. TCP is known for its reliable and in-order delivery. It also supports congestion control and flow control. It provides these services, and also you have to have a connection set up in TCP. However, the UDP provides an unreliable and unordered delivery, and there is no frills extension of best effort IP. So the reliability that UDP provides is the same as the reliability that the third layer protocol, which is network layer protocol IP, provides. And there are some services that neither TCP nor UDP provide. For example, none of them provide guarantees on the delay or on the bandwidth. However, for example, UDP has a higher bandwidth than TCP, and also it provides less delay than TCP, but UDP doesn't guarantee any delay or any bandwidth. So the service of transport layer protocol is multiplexing at sender side and demultiplexing in the receiver side. In order to explain multiplexing and demultiplexing, let's consider this figure. In this figure, we have three hosts: the left host, the right host, and the middle host. The left host runs a process called P3. The middle host runs two processes, P1 and P2, and the right host runs one process, P4. P3 and P1 have a two-way communication, so they exchange messages between each other, and we also have a two-way communication between P2 and P4. Okay, so now we know what processes are talking to what other processes. P3 and P1 are communicating. P2 and P4 are also communicating. Also, as I said in the previous chapter, every process must use a socket which is similar to a door to send its messages out and receive its messages um, from the other side. So you can think of a socket as a door between the application layer and the transport layer. So when P3 wants to communicate with P1, it sends its messages through this socket and receive them again through this socket. So you can think of the middle host as a host that runs multiple processes, and since it runs multiple processes, we need the services that transport layer provides in this host. So let's see how we need transport layer services in this host. In this host, we have multiple processes, P1 and P2, who want to send their messages to multiple processes, P3 and P4. So what happens in this side of the network is when they want to send their messages out, P1 has to send its messages to this socket, and P2 has to send its messages through this socket. So they have the separate sockets, and they have to send their messages out using separate sockets, right? So we need a multiplexing service to handle data from multiple sockets, and P1 has to send its messages through this socket, P2 has to send the messages through this socket. This service of choosing the right socket for the right process is called multiplexing in the server side, in the sender side. Now let's think of the receiving side. Again, let's assume that we are talking about the middle host, because in the middle host we are running multiple processes. In the middle host we have two processes, P1 and P2. P1 wants to receive message from uh, P3, and P2 wants to receive messages from P4, right? So both messages from P1 and from I'm sorry, both messages from P3 and P4 are coming toward uh, the middle process. So the middle process receives multiple messages from P3 and P4. So there should be a service that can demultiplex these messages and deliver them to the right process. So for example, if a message comes from P3 all the way to this host, it has to be delivered to P1, not P2. In the similar manner, if a message is transferred from P4 and receives to the host has to deliver the message to the right process, which is in this case P2. So this service of choosing the right process in the receiving side is called demultiplexing service provided by transport layer. So basically in the receiving side, when you choose the right socket for the right process, you're doing demultiplexing. In order to find out how demultiplexing works, you have to notice that for each segment that we send and receive in the fourth layer, in the transport layer, we have to have a header. The header provides a source port number and a destination port number. The source port number specifies which socket is used for sending the process, sending the socket, sending the segment, and destination port number specifies which socket in the receiving side is used to receive the segment data. So different hosts use the IP addresses and port numbers to direct segments to appropriate sockets. IP addresses are used to address different hosts, but port numbers are used to address different sockets and different processes in a single host. So as you remember from the previous chapter, when we were doing socket programming and we wanted to create a datagram to send it into a UDP socket, we must specify both destination IP address and destination port number. Now you know why we use port number. We use port number for the purpose of demultiplexing. Here we make an example of demultiplexing in UDP. As I said, UDP is connectionless. Therefore, this is an example of connectionless demultiplexing. So again, let's assume that we have three hosts, the left side host, the right side host, and the middle host. The middle host runs P1, which is an application, uh, which is a process, and this process runs an application. And we have P3 on the left side host and P4 on the right side host. So let's consider P1 as an example. In P1, we are sending messages toward two different processes, process P4 and process P3. We sent message to process P3 by the source port number of 6428 and the receiving and destination port number of 9157. So P3 receives the socket. This receives the segments in the socket with port number 9157, and the source port number on P1 is 6428 for the communication between P1 and P3. And we have a similar story between P1 and P4. Again, we need to have a source port, which is again the same number 6428, and because we are working with the same P1 process, and we have another port number, which is a destination port number in this connection between P1 and P4, which is 5775. This port number is used to specify the socket connecting P4 to the transport layer of the host in this side of the network, in the right hand side host. So here we have four different type of messages. This one is sent from P1 and is received sent by P1 and is received by P3. Therefore, the source port number on this message is on this segment is 6428, and the destination port number on this in this the datagram is 9157. For this kind of messages which are sent from P3 to P1, the source port number would be 9157 and the destination port number would be 6428, because here we have 6428 in the receiving process of this message. There are two other types of messages that you can have. One is from P1 to P4, the other is from P4 to P1. This is a message from P1 to P4. Obviously, the source port must be 6428, and the destination port should be 5775, because P4 receives messages on the socket with port number 5775, and the last type of message that we have is from P4 to P1. So the source port number should be set to 5775, and the destination port number should be set at 6428. So in the previous slide, we explained connectionless demultiplexing. Here in this slide, we explain connection-oriented demultiplexing. Obviously, connection-oriented demultiplexing is a bit more complicated because we have to have the socket identified by 4 numbers. One is source IP address, the other is source port number, the other is destination IP address, and the last one is destination port number. Why do we need both source information and destination information? Because we are talking about connection-oriented demultiplexing. Obviously, TCP is the best example of transport layer protocol that handles connection-oriented demultiplexing. So in this type of demultiplexing, the receiver uses all of these 4 values to direct the segment and the data to the appropriate socket. We may have many different TCP sockets that are running simultaneously, and obviously each socket is identified by its own 4 tuple. For each socket we have a distinct 4 tuple of source IP, source port number, destination IP, and destination port number. So let's take a look at an example of connection-oriented demultiplexing. There are 3 hosts in this figure: the left-hand side host, the middle host, and the right-hand side host. In the left-hand side host, we have process P1. In the middle host, we have 3 processes, P4, P5, P6. And then the right-hand side host, we have 2 processes, P2 and P3. The IP address for the left-hand side host is A. The IP address for the middle host is B, and the IP address for the right-hand side host is C. So let's consider an example of the message which is transferred between host A and host B. Let's consider the message that is sent by P1 and is received by P4. Here is the 4 tuple specifying the details of source and destination in this connection. In this connection, the source IP is A because A is the sender, and the port number is 9157. So this port number is corresponding to the socket that you see here. And in the destination side, we have the IP address equal to B because, as I said, B is the IP address of this host, and the port number for this socket, which is connected, in which P4 is connected to, is 80. So this message sent from P1 received by P4 has the 4 tuples A, 9157, B, and 80. So this is an example of connection-oriented demultiplexing. In the client-server architecture of some applications, we may have one process in the server side that handles multiple sockets. In such architecture, the server process, which is P4 in this case, must have multi-threads. Each one runs or controls one socket. So instead of having 3 processes running connected to 3 different sockets, we have 3 threads inside one process, which is P4, that each of those 3 threads run one of these or are connected to one of these 3 sockets.